Hello, this is 5.7. Today we're talking about radical functions. We're going to graph radical functions and inequalities. We're going to transform radical functions by changing parameters. So this has a lot to do with transformations as well. And the joke is, how can you predict how many protesters will show up at a rally? By using a radical function. Radical function that they go to. So some vocabulary for you. Radical function is any function, or like f of x, that has a radical in it. More specifically, a square root function is any function that has a square root in it, which is also a radical. So this one here is more of an umbrella term. And the square root is more specifically, it has to have a square root in it. And I have here discuss inverses of quadratics and cubics. So for an example, a quadratic function would be, I'll just choose the most basic one, f of x equals x squared. Okay, and we know what that graph looks like. I'll go up 4, so at 1 and 1 we have a point, at 2 and 4 we have a point, and it's same on the negative x values. And you have a graph that, come on now, looks like this. Okay, and when you're taking the inverse, remember, you can, they undo each other. So what you could do is you could switch your x and y and solve for y. But your inverse function, I'll write it out, would be inverse of x equals plus or minus the square root of x. And now there's something wrong with this. Your original function, to see if you can take the inverse of it, has to pass the horizontal line test. And that's, if you draw a horizontal line, it can only pass through that line once, and that means you can take the inverse of it. This one, you can only pass through it, or excuse me, you pass through it twice, so you know that the inverse of it is not quite going to work. So, whoopsie daisy. You're fine, you can come in. Okay. So what if we... Anyway, the inverse of this would look something like this, right? And this is not a correct graph because it doesn't pass the vertical line test. So what we can do then is only take the inverse of this portion right here, okay, just the positive side. And then our inverse would be this graph right here. Remember, inverses always reflect over the line y equals x. And so this right here is the square root of x, okay? It doesn't have any negative values here. So this is what the square root of x looks like. For a cubic function, you don't have to write this down. I'm just kind of doing this as an intro. But for a cubic function, let's use, let me go blue. Let's use f of x equals x cubed. And we know what this graph looks like as well, right? We've got, I'll go 1, 2, 3, 1, 2, 3. I'll go up to 9. I'll go down to 9. So at 1 and 1 we have a point. At -1 and -1 we have a point. At 2 we have a point. 2 to the third is 8. So 2, 4, 6, 8. We have a point up at here at 8. And then at -2 we're down at -8, so about right here. And our graph of x cubed looks like this. This is x cubed, right? We're familiar with this one. Now this does pass the horizontal line test. If I were to draw a line anywhere on this graph, it would only pass through it once if it was a horizontal line. So then I'm going to flip it, right? I'm going to switch my x and y values, and my inverse, remember inverses undo each other, so the inverse of this function would be the cube root of x. And this would look something like this. Remember, we reflect across the line y equals x, or y equals eggs, if you remember the joke from that lesson. And this is the cube root of x. So that's what that graph looks like. Okay, so a radical function, an example of that would be the f of x equals the cube root of x because it has a radical, and square root function, an example of that would be f of x equals the square root of x. We kind of already talked about that. Okay, so it wants us to graph this function and identify the domain and range. So this is f of x equals the square root of x. So let's go ahead and make a table of x and y values. And generally we go like -2, -1, 0, 1, and 2, so I'm going to try that. So if I plug in -2, can I take the square root of a negative number? I can't. So it's undefined at any value of x that's negative. Let's try 0. The square root of 0 is 0. Square root of 1 is 1. And then what's the next smallest, largest number that I know the square root right off the top of my head? Probably 4. So I can plug in 4, and the square root of 4 is 2. I could also plug in 9 because I know the square root of that is 3. So then we can just plug in these values. Okay, so at 0, 0 we got a point, at 1 and 1 we got a point, at 4, 2, 4 we got a point up at 2, and then at 9, so 5, 6, 7, 8, 9, we've got a point up here at 3. Like so, and this is our graph f of x equals the square root of x, and it looks like that. If you want to graph it in your calculator, it's good just to familiarize yourself with what it looks like, just so you kind of know visually. That's what it's going to look like on your calculator. And notice there are no negative values for x. So the domain and range. Domain of this bad boy is going to be from 0 all the way to infinity, because on the left side of 0, all those negative numbers, the function is undefined there. So the domain is going to be 0, and we include 0, so we're going to use brackets, to positive infinity. The range, come on now, the range is all my y values. So where does it start? Also at 0. It doesn't go down to negative infinity. So it also starts at 0, also inclusive, up to positive infinity. Okay, so this one wants us to graph f of x equals the cube root of x. So I'm going to do what I did again and make a table of x and y values. And since it's the cube root, right, remember if it's an odd index and a negative radicand, it will have a real solution. If it's an even index with a negative radicand, it will have no solution. So since it's odd, it's cube root, we can go with negative values. So I'm going to go with -8 because I know the cube root of that is going to be -2. And then we'll go with -1. -1, cube root of 0 is 0. Cube root of 1 is 1. And then cube root of 8 is 2. And so what this looks like, we've got, I'll go ahead and mark it up to 8. 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 1, 2, 1, 2. Okay, so down at -8, I've got a point at -2. Here at -1, I've got a point at -1, 0, 0, 1, 1, and then 8, 2. And my graph looks like that. This is f of x equals cube root of x. Domain and range of this function, well, the domain is it goes all the way to -infinity, all the way to +infinity. So -infinity to +infinity. You could also write all values of x. And then the range, it will go down to -infinity and all the way up to +infinity. So you can also write all values of y for range. Okay. So for this one, it wants us to graph the function and identify its domain and range. And we've already studied a little bit of how radical functions can be transformed. So first of all, let's go ahead and graph the parent function of this. So the parent function, I'll say e of x because e is before f. The parent function of this is the cube root of x. And we already know what that looks like graphed because we just did it. So we got a dot here, here, out here, and out here. So this is our parent function. It's cube root of x. And then we ask ourselves the question, what happened to it? How did it get transformed? We've got a 4 out in front here. So that means it was stretched vertically by a factor of 4. So I'm going to take my dots and I'm going to go up, or I'm going to multiply their value by 4. So I'll have to expand my y values here. But this y value is at 1, so we'll go up to 4, 2, 3, 4. Boom. This one is at 2, so we'll have to multiply that by 4 and go up to 8. So we got 4, 5, 6, 7, 8. Boom. This one goes down to -4, which is, where is it? It's right here. And then this one goes down to -8, which is right here. And then this graph looks something like this. And this is vertically stretched by a factor of 4. Then we have this other transformation. It's a 4 that's added to the x. And since it's right up there with the x, it's not added to the whole thing, only to the x. That means it's a horizontal translation. Everything side to side is funky, so instead of going to the right 4, it goes to the left 4. So I'm going to take each of these dots, and I'm going to shift them left 4. So 1, 2, 3, 4. That's where that one goes. This one will go to the left 4. 1, 2, 3, 4. Boom. This one will go to the left 4. This one here will go to the left 4. And then this one will go to the left for 1, 2, 3, 4. And so our final function looks like this. And this is f of x equals 4 times the cube root of x plus 4. Okay, and then it wants us to figure out its domain and range. Goes all the way to negative infinity for domain, negative infinity, all the way to positive infinity, and then range, negative infinity to positive infinity. All right. These are for you to try on your own. Okay, this one, we already did that one actually, so I'm not going to worry about that. That's the cube root of x. This one is the square root of x plus 1. We already know what the square root of x looks like. I know that there's a point at 0, 0, 1, 1, and then 2, 4. And this is what the parent function square root of x looks like. And this function has been shifted to the left 1 unit. So I'm just going to take each of these points in red and shift them to the left 1. And this is going to be square root of x plus 1. And that's what my graph will look like. Okay, so this is just a review of the different transformations of the square root parent function. I'm not going to go over each of them because we already have, but this is on page 368 if you want to look at that. Okay, now we've got more transforming of square root functions. So for this one, it wants us to use x squared as a guide. So describe the transformation and graph. So if our parent function is x squared, this is x squared. Sorry, I keep saying x squared. Square root of x. This is, our parent function is square root of x, and then we've got minus 2. So we know from what we know about transformations is that this was shifted down 2 units, right? So to graph this, I'll go ahead and graph my parent function first. Got a dot here, here, and then at 4 we're up at 2, and that's what the square root of x looks like. But then if we go down 2, I'm going to shift everything down by 2 units. And this is g of x equals the square root of x minus 2. Looks like that. It doesn't want us to describe the domain and range, but I encourage you to think about what that would be if it did ask for it. This one, we've got g of x equals 3 times the square root of x. What kind of transformation is this? There's a 3 multiplied by the whole thing, so that means it's a vertical stretch of a factor of what? If you said 3 in your head, you are correct. So, what I'm going to do is graph the parent function first. See how fast we're getting at these? We already know the points we need to plug in. That's what the square root of x looks like. And then if I want to stretch it vertically by a factor of 3, I'm going to take each of these points on the graph and just multiply them by 3. So I've got a point at 0. 0 multiplied by 3 is also 0, so I got a point there. This one's at 1, so 1 multiplied by 3 is up here at 3. This one's at 2. 2 multiplied by 3 is up here at 6. So right about here. And this is what my graph looks like, which is g of x equals 3 square root of x. Okay, try these ones on your own. Sorry about that. Try these ones on your own, and then I'll go ahead and tell you what the answers are. Okay, so this one is a vertical shift up 1. You could just put up 1, that's fine. And that looks like you have dot here, dot here, a dot here. That's your original function. Shift it up 1. So each of these dots are getting shifted up by 1. And that's your graph right there. This one is a vertical compression by a factor of 1/2. So it's vertically compressed by a factor of 1/2. This one, there's no real short way to write that, so you got to write out all of that. Because if you just said compression, I wouldn't know if you were talking vertically or horizontally or what the deal was. Okay, so I'm graphing my parent function first, as always, and then I can transform it from there. So this is the square root of x. And then I want to vertically compress it, so I'm going to take each of these dots and multiply it by a factor of 1/2. So 0 divided by 1/2, or times 1/2, sorry, is just 0. 1 times 1/2 is 1/2. 2 times 1/2 is 1. And so this is what my function looks like, 1/2 square root of x. And it does look like it's compressed vertically by a factor of 1/2. So that's what we want. Okay, this is a formula for the different transformations of a radical function. And this should be pretty familiar. We've got f of x equals a. A is the coefficient on the outside of the radical. That's gonna tell you if it's a vertical stretch or compression. That's what your a is. Okay. Then you've got your radical, and you've got 1 over b, and that has to be on the inside. And b is going to tell you the horizontal stretch or compression of your function. And it's 1 over b, remember, because if it's horizontal, it's reciprocal. Everything side to side is funky. So if you had 1 over 2, it would actually be a horizontal stretch of 2. If you just had 4, it would be a horizontal compression of 1 over 4. And then you've got parentheses, that's important, x minus h. H is the horizontal shift. And you notice that it's minus h, so if it says x minus 3, you're going to the right 3. If it says x plus 3, you're going to the left 3. And I'm sorry, I don't know which way I'm pointing as to what you're seeing. So I hope that doesn't confuse you if I got that wrong. I was just going by what I can see. What's different about this is that it has parentheses around the x minus h. What that means, if you have parentheses around x minus h, is that you always have to do the horizontal stretch or compression first, then the horizontal shift. If you see parentheses, that means you do the stretch or compression first, then the shift. If you do not see parentheses, it's the other way around, okay? So that's very important. You need to memorize that. Then, of course, we've got the k on the outside, and that is vertical translation up or down. Okay, so more of the same. You can go ahead and try these on your own if you want. This one, we're using square root of x as a guide. we see that we have a coefficient of 2, so that means it's a vertical stretch by a factor of 2. And it's x plus 3 inside the radical, so that means it's a horizontal shift left 3. Okay, I'll go ahead and draw a quick graph. Once again, I always start by graphing my parent function. I got a dot here, and then 4 and 2. And this is my parent function, the square root of x. Then I'm going to stretch it vertically by 2. So I'll go blue next. So here are my values at 1, so that multiplied by 2 is 2. Here are my values at 2, that multiplied by 2 is 4. And that's the stretch. And then I have to shift it left 3. So I'm going to take each dot and shift it left 3. 1, 2, 3. Here we go 1, 2, 3. And up here we go 1, 2, 3. And so this right here is my g of x. That's what it looks like. Okay, this one, what kind of transformations do we have? We've got a negative inside the radical. So what that means is that it is horizontal because it's inside the radical, and it's a reflection. So this indicates a reflection horizontally, so it's going to be across, it's going to be like this, horizontal, so it's going to be across the y-axis. The y-axis. Okay, and then we're shifted down 2. This one will be fun to graph because we've got a reflection. Always start with my parent function. Hopefully you're getting fast at these along with me. So this is my parent function. Then if I'm going to reflect it across the y-axis, I'm going to take each of these dots and reflect it onto this side of my graph. So this one stays here. This one becomes -1, and this one up at 2 becomes a -4. So that's what it looks like reflected. And then we have to shift it down 2. So I'll draw 2 more hash marks. This one is going down 2. This one's going down 2, and this one is going down 2 to be right there. And so this is my g of x. That's what it looks like. All right. Okay, more. I'm going to do these pretty quick. This is a reflection across the y-axis again. And we're getting shifted up 3. I don't think I need to take your time to graph that. This one here is a reflection across the x-axis, okay, because it's a negative out front, that's a reflection. Also, it is a vertical stretch by a factor of 3, and we're getting shifted down 1. And I'll tell you what I'll do is I will graph this on my graphing calculator just to save time, and show you what this deal looks like. Okay, so I've already got my parent function, and then so this is my parent function right here. That's square root of x, and this one is g of x, which is you can see that it's reflected across the x-axis, it's stretched by a factor of 3, and it's actually shifted down, what is it? Shifted down 1. All right. Okay, next slide. Okay, Use the description to write the square root function g. The parent function f of x is the square root of x, or excuse me, f of x equals square root of x, is stretched horizontally by a factor of 2. So this is our first stretched horizontally by a factor of 2, reflected across the y-axis and translated 3 units to the left. I hope you can still see that. It's probably confusing. I'll erase it. Come on. Here we go. Okay. So we start off. We start off with. Come on. Blue. Okay. Back in business. We start off with the square root of x, and it wants to stretch it horizontally by a factor of 2. So if we're stretching it horizontally, we have to put a coefficient inside the radical right up with the x. If it's horizontal, remember it's the reciprocal. So we're going to rewrite it as, I'll just keep increasing my alphabet. So g of x with each transformation. So g of x is going to be the square root of 1/2 of x. Okay? That's stretched horizontally by a factor of 2. Then we need to reflect it across the y-axis. Okay? So we're reflecting it across the y-axis, so that's also horizontal. So that means our negative, so this is h of x, negative goes inside the radical 1/2 of x. So we did that one. Now, I of x, the final product, we have to translate it 3 units to the left. Now remember what I said when I showed you the formula. If you have to do the horizontal stretch or compression first and then the horizontal shift, you need parentheses around this x. Okay? So what this is going to look like is negative 1/2 parentheses x. We're going left 3, so plus 3. And that's your final answer. So that was a really good example because we have to do the parentheses if we do the horizontal stretch or compression first. Okay, try this one by yourself. We've got the parent function f of x equals square root of x, and it's reflected across the x-axis again. So that means we've got across the x-axis. So then we have a negative on the outside of our radical. And then it's stretched vertically by a factor of 2. So that means we've got negative 2 on the outside, square root of x. And then it's translated 1 unit up. So finally, we've got negative 2 square root of x plus 1. Okay. This one is a word problem, and usually word problems we freak out and we're like, this is bad, but I don't think this one is actually all that bad. Special airbags are used to protect scientific equipment when a rover lands on the surface of Mars. I've seen a documentary on this, and it's pretty cool. They've got this little rocket package, and then when it's entering the atmosphere of Mars, all of these airbags in a pyramidal form just sort of explode out of it, and it will bounce safely on the surface. On Earth, the function f of x equals the square root of 64x approximates an object's downward velocity in feet per second. Okay, so we're in feet per second as the object hits the ground after bouncing x feet in height. Okay, so however high it bounces, that's what we plug in for x. The corresponding function for Mars is compressed vertically by a factor of about 3/5. Okay, so they gave us the function of velocity after a bounce on Earth, but on Mars, you got to multiply the whole thing by 3/5. So I'll say m of x, because Mars starts with an m, equals 3/5 times the square root of 64x. That's our little Mars equation. Write the corresponding function g for Mars. Oh, I should have put g. Okay, no m, g. And use it to estimate how fast a rover will hit Mars's surface after a bounce of 45 feet in height. So it bounces off the surface of Mars up to 45 feet, and it wants to know how fast it's going to hit the surface after that bounce. So we have to plug in 45 feet for x. Easy enough. And what I would like to do is, probably much to your annoyance, well, okay, I won't do that just because I said it that way. We're just going to plug it in. So we got g of 45 equals 3/4 square root of 64 times 45. And you know what? I'm just going to go ahead and plug this whole thing into my calculator as is. So 3/5 is the same as 0.6 times the square root of 64 times 45. And that's what it looks like. I've got 6.6 times the square root of 64 times 45, and we get 32.2. 32.2, we're in feet per second. So there you go. Simple plug and chug. Okay, this one is for you to try by yourself. And this is using the same parent function for the gravity of Earth. So that's going to be f of x equals square root of 64x. Okay, but this is going to be for the moon. So it says the downward velocity function for the moon is a horizontal stretch of f, which is this. Horizontal stretch by a factor of about 25/4. So go ahead and read the rest by your own and do it by yourself. Hopefully you did that. If it's a horizontal stretch, wants me to write the function for the moon in h of x, then that means I'm going to take this factor of 25/4 and I'm going to multiply it to what I have underneath the radical, but since it's horizontal, I have to flip it. So I've got actually 4/25 times 64x. And I'll just leave a blank space there for x. Use it to estimate the downward velocity of a landing craft at the end of a bounce 50 feet in height. So that's my x, so I plug in 50 there. Okay. Now I could plug this into my calculator, or I could see if I can simplify it a little bit. So let's go ahead and do that. So what we've got is, I'll rewrite this as the square root, and then I'll write everything on this even playing field. So we've got 4/25 times 64/1 times 50. Now I've got a 50 on top and 25 on the bottom, so that can cancel out and just become a 2. I've got a 4 right here, and I already know that the square root of 4 is 2, so I can bring a 2 out. I've got a 64 right here, and I already know that the square root of 64 is 8, so I can bring that out. So this becomes 2, because that was my 4, times 8, because that was my 64, times the square root of 2, which is, of course, 16 times the square root of 2. I'm going to plug that into my calculator and see what I got. 16 times the square root of 2 equals, see that at the bottom there, 16 times the square root of 2 is 22.6. 22.6 feet. a second. Inequalities. Wants us to graph the inequalities. We've had lots of practice graphing these radical functions. Now we got to graph the radical inequalities. So, y is less than and not equal to, just less than, uninclusive, square root of x plus 2. So we know what this graph looks like, right? Square root of x. I've got my point here. I've got my point here. That's my parent function. And then I have to shift it up 2. So this goes up 2. I'll do it in blue. This one goes up 2. Oops, that was 3. This one goes up 2, and this one goes up 2, and it looks like that. Now, it wants to know what is less than this function, x squared plus 2. So that means we have to shade in everything underneath our graph. So I'm going to shade in everything underneath square root of x plus 2. And since it doesn't actually include square root of x plus 2, I have to draw this as a dotted line. Remember that? So I'm going to draw that as a dotted line. And that's what that looks like. I hope you can see that. Okay. These are for you to try on your own. This one, we've got y is greater than the square root of x plus 4. So let's go ahead and graph our function here. I'm going to graph my parent function first because I like to do that. So we got a dot here, here. So that's my parent function, and then I have to shift it to the left 4. So we got 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. And it is not inclusive, so we'll go ahead and draw this as a dotted line. And then it's everything that's above square root of x plus 4. So that means I'm shading in everything that's above it, like so. You're not going to shade anything on this side, though, okay? Because x has no values to the left of -4. So make sure you don't shade anything past this point right here. Okay? And that's what that is. This one, we've got y is greater than or equal to the cube root of x minus 3. So cube root. We haven't done one of those in a while. I'll go ahead and do this just so we remember. We can plug in -8, and we have a value at -2. We can plug in -1. We have a value at -1, 0, 0, 1, 1, 8, and 2. So at -8, we're down here. Oops. Down here at -2, -1 and 1, 0, 0, 1 and 1, 8 and 2. And this is my parent function, and then I need to shift it to the right 3 units. 1, 2, 3, 1, 2, 3. This one's going to the right 3, to the right 3, and to the right 3. Boom. Boom. I'll go ahead and erase my parent function to avoid any confusion, because that was just for a guide. Okay, so this is my graph, and it wants everything that is greater than or equal to y. So in this case, I can just do everything. I don't have to stop because there's no values of x this way or that way that I can't do, so I can just do everything. This is a solid line because it's inclusive, and that's what it looks like. Okay, that's it. Happy math.